So we get a loose, let's say, a boundary of each and every one of these points of that particular surface. Then you have to do some neighborhood definition, meaning for every point, what would be the number of points around every point that would be able to provide you with some information about the properties of the surface that that point belongs to. This is why we're not looking at only one point, right? We're looking at many points. Once we look at many points, what we're getting from those many points is the opportunity for us to estimate the pattern of that particular surface. For that, we need to know whether I'm going to get 5 centimeters around this or 50 centimeters around this. What dictates that? That by itself is what we call a neighborhood definition. That there are many methods. I have a method as well that is very suited for planar and curved surfaces specifically. So it tries to find all of the neighbors that maximizes planarity or linearity. This way, those ones that are planar surface grows a bit larger, and those that are curved grows a bit smaller. This would be able to provide us with the opportunity to actually differentiate between the planes and non-planar surfaces. Then what I do for that particular neighborhood, I extract that out. And there's a reason why I have to do this. One is, if I have all of the information related to the errors associated with every point within a particular neighborhood, I would be able to simulate those points on that neighborhood again and again and again, and identify how this particular planar surface is going to have to behave, right? There's a major problem here, is that if I could determine that in a closed form fashion, I would be able to say every planar surface here, or if these points belong to a planar surface, they have to have a root mean squared error difference that constitutes with points that follow a planar surface and that follow the measurement error. That is not going to be estimated in closed form. Each of these are different error ellipsoids that you have to then find the best fit plane of all of these error ellipsoids there. The distribution of the planar surfaces and the confidence interval is going to be significantly challenging. Okay, so what do? I basically go and simulate these points. I say, if the best fit plane to these points that are within that error ellipsoid that we talked about for each and every one of these points, similar to the Monte Carlo simulation we talked about last year, right? Last semester, that for scheduling, in order to get the distribution, we get different points, random. We do the same thing, this time from a 3D distribution. We do it many times, and then every time we go and we estimate the RMSE. Based on the distribution of these points and the distribution of the RMSE, we can then go and figure out where the distribution of the real RMSE is versus the distribution of what we would expect if these points would actually follow the measurement errors that we have accounted for within our error ellipsoid. Cylinder hypothesis looks like this. And then from those cylinders, or I assume that this is a planar surface and I fit the best fit plane here, which one would be accepted, which one would be rejected? So this is a curved surface, right? We know it, we can observe it. But algorithm doesn't observe it, doesn't know it, right? So I'm trying to figure out whether it does belong to this cylinder that is a hypothesis, or does it belong to a planar? If it were to belong to a planar surface, this magenta would have been the distribution of the points, not how it's going to look like after I basically do the transformation. Because this is actually the best fit plane to all of these blue points here. So if we take a look at, and we simulate this, let's say 50 times, this is how it's going to look like with the points that are on the cylinder and the expected value of those points, or let's say the RMSE of all of those points for each and every one of those simulations is within that. If you want to take a look at that, how the magenta is going to orient itself around our planar surface is going to be something like this. And then where we have our RMSE total for our original points is going to be way outside of that distribution. And it shows it, right? It doesn't follow a planar surface pattern. Well, we know that this, let's say, HSS member consists of a planar surface, a curved surface that represents a cylinder, and then another planar surface, okay? We go and we see which one of these points belong to these planar surfaces, and if it does belong to the planar surfaces, we attach it together, and then we perform the ICP based on that. Based on the ones that actually have a characteristics of those particular templates that we want to match it to. Okay, another one is something that I've recently came up with, and this is for any type of shape, as long as the shape itself is not, the dimensions of it is not going to change significantly. That means that, let's say, this I-shaped member here is not going to be slanted in this way. It's going to still remain an I-shaped member. But we are having placement issues. This way, I have a method that I basically approximate the cross sections of these, or the whole 3D, it could also be applied to that, as a trigonometric polynomial. So a bunch of terms that would very accurately go and basically fit to this model for surrounding. And then I have a method that basically does a least squares adjustment, basically similar to what we did with the plane fitting, but this time I got the objective function of the orthogonal distance between every point and every trigonometric polynomial that exists. So I have a closed form solution for that. Then once I do that, then I have to get an initial value with respect to our orientation and rotation to be able to orientate this and train our model to make sure that we are basically going to be converging to a correct result for our registration. How do I do that? I utilize that using a AI-based optimization, particle swarm, genetic algorithm, Bayesian optimization, different types of methods that you can utilize. Once you have that, then I do a final adjustment at the end of it as well. How does it work? So I give it a very exaggerated transformation. So this is how it's going to look. That means that assuming that this is our I shape and this is how, from the top when you're looking at it, that's how the point cloud looks like. Even our eyes would not be able to identify this, right? And if my method can recover this, that means that it would definitely recover normal construction errors. That's why I do it this way, not because this necessarily happens in a construction project, but because if it can actually survive this, then we can be rest assured that for smaller errors that we are expecting, it would definitely do that. So I use particle swarm in this case, and you see the convergence is pretty much when the mean particle score and the best score is getting closer together. As you can see, it's pretty much recovered it, right? And this was only possible using the formulations that I did. And then afterwards, I do a robust fit to essentially finalize. This is going to be in 2D, so any type of adjustments in this direction and anyone in the translation direction. And then from that, it only takes all of the points that are surrounding this object, and then it gives us some results as well. So at the end, I was able to get the results of these with 0.4 degrees in terms of orientation and 0.6 millimeters in terms of the translation, compared to the best that would be possibly available. Now, this also is a bit misleading because it's actually better than this, because once you convert basically where the final result is, you can actually play a bit with rotation and translation to make it better. Really, the result is well within tenth of a millimeter, real accuracy and real result between them, right? And that's basically what you'll get here as well.